Welcome back. Last time we talked about differential equation. Today we're going to discuss a specific type of equation that we can solve. And that's the separable equation, section 3, chapter 9. First, let's see what is a separable equation. If we have a first order derivative, so this is for the first order derivative, dy over dx, equal to product of two functions where the functions are function of x multiplied by a function of y. Then we can call this a separable equation because the two functions are separated. They're not interconnected within each other. Assuming that f is not 0, if f is 0, then you have a derivative equal to 0, which basically means that the original function was a constant. So assuming that f is not 0, you can move the f to the denominator and write it as gx divided by some hy function. But hy is basically the f in f to the power -1 or 1 over f. So we can write the dy over dx equal to gx over hy. If we do this, then you can do some cross multiply, and what we get is hy dy equals to gx dx. And then if we integrate both sides, on the left side what you get is some function of y, capital H of y. On the right side what you get is some function of x. And you have a relation between y and x plus some constant c. Well, you don't need to have constant c on both sides, but what you get is basically a function of y represented based on a function of x. Then you can solve for y. Okay, so what do you get throughout the solution if you're dealing with the separable equation is that the family of solutions. Because this C basically means you can pick the initial condition to be whatever you want. So you will get a family of solution. Unless they say specifically based on this initial condition, then you will find a particular solution. Here I wrote a couple of examples to go through. And the idea is very easy. So given differential equation dy over dx equals x squared over y squared, you notice that we have a function of x divided by a function of y. These two are separated from each other. Then with the initial condition y equals 0, we want to find the particular solution to this equation. First, let's find the general solution. So we have dy over dx given as x squared divided by y squared. So if you cross multiply, what you get is y squared dy equal x squared dx. And if we integrate both sides, you get integral of these two. So this results in the integration of y squared dy would be simply y cubed over 3. Integration of x squared would be x squared over 3. And assuming that you have some constant on the left side and some constant on the right side, you can assume that the constant is simply on the right side. Move everything to one side. Then you can multiply 3 to the whole equation. What you get is y cubed equals x, this is supposed to be x cubed plus 3 times c. You can write this as a new constant k if you want. Then what is y cubed? Y would be cube root of x cubed plus k. And we found the general solution to this differential equation. To check that, to see if this is the solution, you can always take the derivative and replace it back into the equation to see if it really is the solution. If you do that, you'll notice that this is the solution. But now this initial condition is given, which means that we want to find the particular solution. So at the y equals to 2 if x is given 0. So this is, if x is 0, we know that y must be equal to 2. So 2, if we replace 2 into the equation, what you get is 2 for y and 0 for x. You'll get 0 cubed plus k. You can figure out what is k. So therefore, sorry about that, let me write it better. Therefore k would be, you can cube both sides, 2 cubed is simply 8. So now I can say the particular solution that I was looking for is y equal cube root of x cubed plus 8. That is the particular solution to this differential equation. You notice it's not too complicated. You just need to make sure that it's a separable equation, and throughout that you can always move the y's to one side, x's to one side, and solve the equation. Here's another one. We have differential equation dy over dx. Let me shift this up a bit in case if we needed more space. It's not always necessary to find it in terms of y. If they ask you to find in terms of y, otherwise you can just leave it as it is. But let's say they ask you to find out what is this solution to this equation looks like. So we can multiply dy dx across, this times that. You notice the numerator and the denominator, they're totally different in terms of function. This is a function of x in the numerator. You have a function of x in the denominator, you have a function of y. So we have 2y plus cosine y dy equal 6x squared dx. Now if you integrate both sides, so the integral 2y plus cosine y dy equal integral of 6x squared dx. What would be the integration on the left side? It would be y squared plus the integral of cosine is sine y. On the right side you will get the integral of 6x squared would be 2x cubed plus some constancy. Here is the issue. It's not that easy to figure out what is y by itself. So we leave this as the general solution. Because solving for y is not easy. You can try to solve for x, but you cannot simplify the function of y. So we can say this is the general solution to that equation. It's a curve, it's not specifically a function. Very simple, easy, just make sure that you integrate correctly. And here's another example. What if it was not in the form of division? What if it was, by the way, sorry, this is y prime, only first derivative. What if it was multiplication? You have y prime equals to x squared times y. So you can always do this, say dy over dx instead of y prime equals x squared times y. And if you remember, I said you want to move the y's to one side and x's to one side. So you can do cross multiply. So you have dy equal x squared times y dx. And since I can get rid of this y by dividing it, I'll write it as 1 over y dy equal x squared dx. This is what we did. We multiply both sides by 1 over y just to simply get rid of this y here. So on the left side I have a function of y multiplied by dy. On the right side I have a function of x multiplied by dx. Totally separated from each other. Now at this point you can integrate both sides. Integral 1 over y dy must equal integral x squared dx. And what is the integration? The left side would be ln absolute value of y. On the right side you have x cubed over 3 plus some constancy. Now here you can solve for y. What would be y? Y would be absolute value of y would be, if you raise both sides to the power e, if you do this e to that power, e to this power, what do you get is y equals, sorry about that, y equal e to the power x cubed over 3 plus some constancy in the exponent. And this could be simplified to absolute value of y equal e to the power x cubed over 3 multiplied by e to the power c. E to the power c, e to some power of constant. They're both constant, so you can assume that this is some constant. E to the power c. This is simply a constant. You can call it k if you want. So this would be some k multiplied by, I can call this a k. Some k multiplied by e to the power x cubed over 3. And what would be y in this case? Because we want to get rid of the absolute value, y would be plus or minus k e to the power x cubed over 3. You notice that always one of the easy solutions to check is that to see if 0 is a solution. So here, in case if you check, you can let k to be 0, then y equal to 0 would be a solution to this equation. In the other cases, if you let k to be positive or negative number, doesn't really matter. When you do the plus or minus, it should satisfy this equation. So you have this family of solutions as your solution to the parabolic to the separable differential equation, y prime equal to x squared times y, as a test just to make sure that you check your solutions by replacing it back into the equation to see if it works. Okay, so every other example is very similar to these. One more topic that I want to mention in this section is the orthogonal trajectories, which means that sometimes you're given a family of curves, which means there is a constant involved somewhere that you don't know. And here, for example, let's consider these blue curves to be the family of curves. And the question is, can we find the curve that goes through all these curves and it's orthogonal to it? That's what is the orthogonal trajectory. Basically, we were looking for a orthogonal curve that is orthogonal to all those to all the other families of curves. Here, if you look at the circle, every straight line that passes through the origin would be orthogonal to this circle. So here, every angle is 90 degrees. So every line y equal to mx would be orthogonal to this family of circles. By the way, my circles doesn't look that neat, but so how do we find such orthogonal curve? How do we find the equation of such orthogonal curve? So first, notice that if we know that the slope of either one of these curves, these blue curves, if we know the slope of this curve, which means we know dy over dx. So if we know the slope of the curve, we know the orthogonal slope would be basically m orthogonal. This means orthogonal is the same as -1 divided by the original m. Because the product of the orthogonal and the slope of the orthogonal curve and the original curve, the product of those two slopes must be -1. You know, two lines are orthogonal if their product, their slope equals to -1. Or one is the reciprocal of the negative of the reciprocal of the other. So in this case, the red curve must have the slope of negative dx over dy. So if we find the slope of the curve, the blue curves, then we can find the slope of the red curve by taking a reciprocal, multiplying a negative. Then we have a differential equation to solve. We can find the equation of the curve satisfying that differential equation. So here, as an example, let me go back to the color red. Find the orthogonal trajectories of the family of the curves y equal to k, x equal to ky squared. So this is some families of curves. For example, if you let k equal to 1, what do you get is this parabola, which is sideways, as if it's k equal to 1. If k equals to 2, then you would get something that grows faster, maybe something like this. It's still parabola shape. If you pick k to be negative, then you will get the curve to be the other way. So you'll have a bunch of families of these parabolas. And what you're looking for is a curve, maybe one, maybe multiple, that is orthogonal to these families of red curves. I should have drawn this x and y axis through a different color. Say here. So we're looking for an orthogonal curve or curves to these parabolas. First, let's find out what is dy over dx. So x equals to ky squared, where k is a constant. If we take a derivative with respect to x, we get 1 equals derivative on the right side would be k times, you have to implement the implicit differentiation or chain rule, 2y times dy over dx. So hence I can find that dy over dx is simply 1 divided by k times 2y, or 2ky. Okay, so now what is the what can we do about the slope of the orthogonal? By the way, you can simplify this a bit. If you want, you can multiply, you can replace k. What do we know about k? K is x divided by y squared. You can replace k with x divided by y squared in this equation, and I can say dy over dx would be simply 1 divided by 2 times, instead of k, I replace x divided by y squared multiplied by y, which simplifies to 1 divided by 2x over y. You can move this y to the numerator, so it would be y divided by 2x. So I found this dy over dx turns out to be y divided by 2x. This is for the red curves, for the parabolas. And what do we know about the orthogonal curve? We know the orthogonal curve has to have the slope of dy over dx. This is for the orthogonal curve. The slope must be negative 1 divided by the given slope. So it would be reciprocal of that multiplied by a negative. So negative 2x divided by y. And now we have a differential equation. We want to find out what is y. So throughout this process, I can now go on and solve. What do we get is solve this equation. We get dy times y must be equal to negative 2x times dx. And what is the left side integration? So if you integrate both sides, you get y squared over 2 equal negative 2x integration would be x squared negative plus some constant c. So what we get as an equation is basically y squared divided by 2 plus x squared equals c. If there was no denominator 2 here, what you have is basically equation of a circle. But with this denominator, it's just instead of giving you a circle, it will give you a elliptic or ellipse. So basically what you get is a bunch of ellipses here that are stretched out maybe along the y axis. So this is maybe one of them. If you pick C, for example, 1, for example, if you pick C to be 2, then you will have this other ellipse. So what you notice is this angles created here must be 90 degrees. So which means that these curves are orthogonal to one another. And this is maybe one of the useful tools for the separable equation. If you want to find the orthogonal trajectories, then if it's possible to have a separable equation, it's easy to do it throughout this process. Okay, I'm going to stop at this point and we will continue on differential equation next time.